Methods? 23 stations were selected to analyze the temporal variability of summer, June to September, temperature and rainfall, Table 1 and. The selection of these stations was primarily based on the availability of continuous measurements of temperature over the period from 1950 to 2010. This period was selected in order to analyze the largest possible number of stations. Prior to 1950, there were very few stations in Quebec where temperature and rainfall was measured. Since 2000, to streamline the measurement of hydroclimate variables in Canada and Quebec, many weather and hydrometric stations were shut down. For this study, all stations for which hydroclimate variables have been measured quasi-continuously for at least 50 years during the period from 1950 to 2010 were used. Summer temperature and rainfall data were taken from the Environment Canada website, http://www.climate.weatheroffice.ec.gc.ca/ viewed in March 2016. For each summer month, a series of maximum daily temperatures was produced. Some data from analyzed stations. Location of stations analyzed. As far as El Niño events are concerned, only events of differing intensities, weak, moderate, strong, and very strong, following the NOAA classification, were selected. From 1950 to 2010, 22 El Niño events were recorded, including 11 events of weak intensity, 1951 to 1952, 1952 to 1953, 1953 to 1954, 1958 to 1959, 1968 to 1969, 1969 to 1970, 1976 to 1977, 1979 to 1980, 1994 to 1995, 2004 to 2005, and 2006 to 2007, 6 events of moderate intensity, 1963 to 1964, 1986 to 1987, 1987 to 1988, 1991 to 1992, 2002 to 2003, and 2009 to 2010, 3 events of strong intensity, 1957 to 1958, 1965 to 1966, and 1972 to 1973, and 2 events of very strong intensity, 1982 to 1983 and 1997 to 1998. Based on Oceanic Nino Index, ONI, the running 3-month mean SSD anomaly for the Nino 3.4 region, values, an event is considered to be an El Niño event when the ONI values for 5 consecutive overlapping 3-month periods are at or above the plus 0.50 anomaly. The threshold is further broken down into weak, with a 0.5 to 0.9 SSD anomaly, moderate, 1.0 to 1.4, strong, 1.5 to 1.9, and very strong, greater than or equal to 2.0, events. However, for this study, rather than using ONI values, Southern Oscillation Index, SOI, values were used because they are available and widely used in the scientific literature. Moreover, using SOI values makes it possible to readily compare the results of this study with those of previous work. It is, however, important to note that SOI values associated with the different El Niño intensities are negative because they are derived from differences in pressure, whereas ONI values are measurements of surface water temperatures of the tropical Pacific Ocean. Be that as it may, the 2 types of indices, SOI and ONI, lead to the same results due to their strong correlation. For each of the 22 El Niño events, the following 6 seasonal mean values of SOI indices were then derived. AMJ1 is the mean SOI value for the months of April, May, and June of the previous years, JAS1 is the mean SOI value for the months of July, August, and September of the previous year, OND1 is the mean SOI value for the months of October, November, and December of the previous year, JFM is the mean SOI value for the months of January, February, and March of the current year, AMJ is the mean SOI value for the months of April, May, and June of the current year, and JAS is the mean SOI value for the months of July, August, and September of the current year. SOI index data were taken from the NOAA website, National Oceanic and Atmospheric Administration, http://www.cdc.noaa.gov/climate-indices/list, viewed on November 23, 2017. Indices for the previous year, when the El Niño event is ongoing in the Pacific Ocean, were included because the influence of El Niño events on climate in Quebec is observed after a lag of at least 6 months. Statistical analysis of data was conducted in 2 steps. In the first step, the Spearman's rank correlation coefficient and Mann-Kindle test were used to constrain the long-term trend of the temporal variability of maximum daily temperatures for the 4 summer months. Both tests are widely used in climate science and have been described in many articles, for example. Because both tests yielded the same results, we only present results obtained using the Spearman's rank coefficient test. It is important to note that the series analyzed did not show any autocorrelation. Spearman's correlation coefficient is calculated using the following equation, where n is the sample size, number of years during which streamflow was measured, and y is the rank of the value of streamflow measured in year I for streamflow values ranked in order of increasing magnitude. The test critical value is calculated using the following equation. The null hypothesis, absence of a significant trend, is rejected if the value of Ts is higher than the value appearing in the table of students' t-values for a given probability level within 2 degrees of freedom. The last step consisted of correlating maximum daily temperatures for the 4 summer months with the 6 SWA series for the 22 El Niño events of differing intensities. It is important to note that years that do not match the years of occurrence of an El Niño event were excluded from this analysis so as to only look at the influence of El Niño events on the interannual variability of summer maximum daily temperatures. No previous study has considered El Niño events exclusively. In this study, only the simple correlation method was used because multivariate analysis methods, canonical correlation analysis and redundancy analysis, did not yield conclusive results due to the relatively small sample size, 22.